Good evening, and thank you for joining us for this live streamed astronomy presentation, The Night Sky in January of 2021, with Paul Arndt. I'm Rick Wallace with the Pajarito Environmental Education Center, or PEEC, located in Los Alamos, New Mexico, and I will be the moderator for today's talk. Tonight's talk is being recorded. We're able to offer programming at this time because of our wonderful members and donors, so we'd like to thank you for your continuing support. So our presenter tonight is Paul Arndt. Paul's formal education includes an undergraduate degree in geophysics and a graduate degree in physics. Before coming to work at Los Alamos, Paul did R&D for a variety of industrial companies with product applications in nuclear fuels, aerospace, glass manufacturing, and metallurgy. At the lab, he focused on developing materials for visible and ultraviolet optical coatings, microwave cavities, high-temperature superconductors, semiconductors, and carbon nanotube composites. With no formal training in astronomy, he remains an avid amateur with a constantly moving goal of remaining a few steps ahead of his precocious grandchildren. All right, let me turn it over to Paul. Let me just unmute, and hopefully Paul can get his video on.
Got it?
Okay.
Rick, can you hear me?
We can hear, I've got you. We don't have your video. I don't know if that's important.
Just a minute. You don't have my video. Okay, hang on. I didn't stop sharing.
Yeah, we still have your slide. That's just fine. I just didn't know if you wanted the video.
Oh, you want to see my face. Okay.
There you go.
You've got it. All righty. Okay, Rick, thank you very much for the introduction. And I'd like to also thank all of the attendees out there in agreeing to watch our show for the night sky in January. I hope you find it rewarding, and this will stimulate you to go outside as well. I always ask the webmaster to move this slide forward. Hello, there we are. To ask folks to at least look at the evening sky map, if not download it. It looks fairly complicated for new attendees, but don't be overwhelmed by the amount of details seen here. Our presentation will concentrate on that yellow region in the southeast quadrant of the January evening sky. And even there, not all of the items seen there will be, we just can't do everything in an hour's time. We're just going to take a few bites out of the apple. The sky map also, as you can see, labels constellations, brighter stars, star clusters, etc., other objects of interest for you to peruse throughout the month. The calendar on the left is needed because it makes pointers mostly discussing the moon's positions or conjunctions near other bright objects through the month. And there's a few other pointers made about planetary conjunctions, and we'll be discussing a few of those. On the second page, we've got, depending on your equipment, interest level, etc., ways you can look at many of the celestial objects listed here on the right-hand side over, as I said, several or more evenings. This will enhance your familiarity with the overall night sky, we hope. Okay, let's get out of this real quick and go to our full dome presentation. We'll go back to a PowerPoint slideshow towards the end. Takes a few seconds for this Nightshade software to load. And what I want to do is point out to you that similar to the sky map from skymaps.com, the north-south cardinal directions are on the vertical axis and east-west are on the horizontal axis. And in addition to that, we have on the southeast side of the screen a date and time stamp, and it corresponds roughly to the time we have right now. what I'd like to do is back up the time a little bit over an hour and a half. And we're going to stop there. And right around about 30 to 35 minutes after sunset, in the southwest portion of the sky, you have actually two bright objects seen here, and one slightly dimmer object. And those of you that have been watching our shows for the past few months, I do hope you realize that the top two objects here are Jupiter and Saturn. And I'm going to pull these up to the center of the screen and get rid of the atmosphere so it doesn't interfere with what we want to point out. We'll zoom in just a little bit. And this other object, Saturn is to the right of Jupiter. It's roughly 8 to 10 times dimmer than Jupiter. And the bright object below, I hope some of you have guessed, is either Mercury or Venus, but Venus right now is in the morning sky. So this object right here is Mercury. And what I'm going to do is advance the clock a day to tomorrow evening, roughly 30 to 35 minutes after sunset, and one more day to the 10th. And right around here, we've got a triple planetary conjunction. These are fairly rare items. They occur once every several years. The last one was, instead of Jupiter, Saturn, and Mercury, it was Jupiter, Venus, and Mars back in October, late October. The two planets, Jupiter and Saturn, will continue to move towards the sun or the western horizon, while Mercury is coming out from behind the sun and is going to continue to rise higher and higher throughout the sky for the rest of the month until the 23rd. Mercury is roughly 1/2 the brightness as seen from Earth of Jupiter. So let's start the date stamps and go forward. You can see I've held Jupiter steady in the sky, but Jupiter and Saturn really are moving towards the sunset. And by the middle of the month, they're going to be disappearing below the western horizon. Mercury is going to continue to advance in the skies. And by the 23rd of January, it's going to be at its maximum extent or elongation, as astronomers call it, from the sun. And instead of having to use binoculars to look for Mercury, as we'll have to tomorrow evening or the evening after, you'll be able to see it in the full night sky. All right, let's back off here. Whoops, wrong way. There we go. And we're going to be looking at another planet. See this ruddy objects toward the middle of the screen and slightly below the center. I hope many of you recognize that that is the planet Mars, which we've been talking about for the past several months. Let's pull that up to the center of the screen. We're doing this for a reason, as you'll see in a minute. By the way, I forgot to mention, you're going to need binoculars to look at that planetary trio, because you might be able to suss out without binoculars Jupiter and Mercury, but definitely you'll need binoculars to see Saturn because it is so dim and stuck in the evening twilight. All right, we've got Mars here, and above Mars is a fairly dim star on the 19th. And below Mars, there's an object that is approximately the same brightness as seen from Earth as this dim star. They're approximately the brightness of Jupiter's moon. So if you can see Jupiter's moons with your binoculars, you will see these two objects easily. This object down here is Uranus. And Mercury passes Uranus roughly every 2 years. We talked about this 2 years ago in February of 2019, But if you want to see Uranus without having to resort to a telescope, see it with binoculars, this is your chance to do it because Mercury is your guidepost, if you will. Let's advance the clock a little bit. Actually, let me keep Uranus still because it doesn't move in the sky relative to Mars. And we're going to advance the clock a day and another day. And on the 20th, 21st, Uranus is going to be roughly 2 degrees below Mars. It'll be at its closest for this year. And if you ever want to see Uranus in binoculars, this is your chance. The other thing you can do if you have a modest telescope is to train it on Mars and then go move it down slightly. You'll be able to see these 3 objects with binoculars, but with a telescope, you will not, unless you have really, really low magnification. So what you want to do is use modest magnification on your telescope, 40 to 60 to 80 power, and find Mars and then move 2 degrees south and you'll see Uranus. And with a telescope, you'll see Uranus as a disk and it's going to, it'll appear as a disk and it's going to be about 2.5 times the diameter of Mars that Mars was in your telescope. It won't appear as a disk in binoculars, not at all. All right, let's back off here, go to the full night sky. And let's advance the clock to about 9 p.m. Oh, oh well. I'll get rid of that oscillating marker in a minute. All right, we went a little past 9 p.m., but we're going to be looking at what was the southeast quadrant in that sky maps right here. And I'm going to move this bright object to the center of the screen. And I hope some of you recognize, let's zoom in just slightly, what constellation this bright object is in. It's in the constellation Orion. The bright object is Betelgeuse, red giant star. It's a ruddy red color, and it's in one of its brightness as it appears to us here on Earth makes it in the top 10 of all the brightest stars in all of the night skies. This other bright star on the lower right-hand side of the constellation Orion is Rigel. And it also fits in that category of being within the top 10 brightest stars in all the sky. That's why our eyes are generally drawn to Orion because of the 2 bright objects, but also these other 5 stars, 3 in the belt and 1 just opposite Betelgeuse on the right, the star Bellatrix, and the other one opposite Rigel here on the left is Safe. Both of these, by the way, Safe and Rigel mean foot, and Betelgeuse means shoulder or armpit. Bellatrix is a female warrior. At any rate, this is an hourglass sort of pattern. And even in urban skies with light pollution, you should be able to suss out or pick out Orion. You won't be able to pick out the dimmer stars in light polluted skies, but you should definitely be able to see at least these 5. And Orion, if you ask people what their favorite constellation is, Orion tends to be the number 1 for probably more than 90% of the population because it is indeed so easy to find. The other reason it is so bright is that the other 5 stars besides Rigel and Betelgeuse is these 5 stars are in the top 100 stars, brightness of top 100 stars in terms of brightness as seen from Earth. So 7 of the top 100 brightest stars as seen from Earth are in this particular constellation. It's really the brightest constellation in all of the heavens. The thing I'd also like to point out about Orion is I call it the Swiss Army knife of constellations because it points to so many other bright objects. If you take the belt stars and point from the upper right-hand side to the lower left-hand belt star, this other star right here is, as it appears to us from Earth, is the brightest star in all the heavens, Sirius. And you can see the labels pop up as I, up here on the upper right-hand quadrant, as I click on these stars. Sirius, #1 in terms of brightness, and it also is the parent star of a fairly bright constellation, not quite as bright as Orion, but 4 other stars in this constellation, which is Canis Major, the big dog. And let's pull up the constellation lines. You can see that it does mimic a dog to some degree. Orion is supposed to mimic a hunter. You might have trouble seeing that, but if I put the artwork up, you should see it quickly. He has a club, and as we'll see in a few minutes, he's fighting off a Taurus the bull here on the right. Okay, let's get rid of these. And let's get rid of the constellation lines real quick. And we just want to point out some other stars that you can, and objects you can see with using Orion as a guidepost. Take the belt stars, go to the upper right-hand direction, and this bright, ruddy, bright star you see here is Aldebaran, and it's in the top 15 in terms of brightest stars in all the skies. And beyond that, you've got this cluster of dimmer stars, which by themselves are comparable to the brightness of the stars in the Big Dipper, but all together they form an attractive concentration of light that generally draws people's eyes towards them, and that is the Pleiades. I think many of you have looked at that in the past through binoculars, and we'll talk about that a little bit more in a few minutes. But let's continue with using Orion as a guidepost. If we take Bellatrix and Betelgeuse and take a line off to the left, it points to another one of the top 10 brightest stars. It's called Procyon. It's in the constellation of Canis Minor, the little dog, and its lines are just 2 lines, 2 stars long, very short, and some folks have called this, instead of the big dog, it's the wiener dog of the constellations. These 2 hunting dogs are supposed to be Orion's companions in mythology. Another bright star that Orion points to, if we go from Rigel to Betelgeuse, continue the line up, we get to this ruddy looking, not real ruddy looking, kind of yellowish star, Pollux in the constellation Gemini, and its brother star is Castor. And the final real bright star, this portion of the sky, is this one directly above Orion. So when Orion is near the north-south meridian and we're looking towards from south to north, you'll see this very bright star, Capella. It's #6 in terms of brightness. So if we bring up the names of these stars, let's do that. These 7 listed here, and finally Castor, which is here. These 7 plus Castor constitute 8 of the 25 brightest stars in all the heavens. So basically 33% of the brightest stars in the top 25 are right here. That's why our skies in the winter constellation, winter skies, are just so brilliant to us, because you got so many bright objects to look at, in addition to bright constellations. So just for our own edification, we'll bring up the constellation lines. We'll bring up the artwork. Whoops, let's bring up Taurus the bull. You can see the fiery eye of the bull is charging towards Orion, and his faithful companion hunting dogs are giving him encouragement, but not jumping out in front. And these constellations, let's just bring up the names real quick. get rid of the artwork quick. Auriga, the charioteer, and you could think of it being a charioteer because this roughly mimics a, I guess, Fred Flintstone wheel. Gemini, the twins, Canis Minor, Canis Major, etc., etc. Let's get rid of the names and the constellation lines. Whoops, sorry. And we're going to talk a little bit, but we're going to do it in much more detail in a few minutes about this winter circle or winter constellation. And if we start from Sirius and go around in a counterclockwise direction, you can see that it roughly forms either a winter circle, as some people call it, to Aldebaran, to Rigel, or a winter hexagon. Not quite a perfect hexagon, but a hexagon. And in the middle, almost centered of it all, is Betelgeuse. So that's one good reason to get out there in the evening skies. Let's start to look at some objects here, starting with the Pleiades. And let's center it and zoom in a little bit. Let me get rid of this wheel for a minute. Keep zooming in. And this has to be included among some of the most spectacular binocular fields in the entire sky. The age of this particular cluster of stars is 120 million years, and its distance is about 440 light years. And where do we get those numbers? Well, I'm going to promote the show for next week. Galen Gisler is going to be giving a talk, and that's going to discuss how these and other properties of stars are determined by looking at the light of the stars. The other properties astronomers can calculate or figure out are chemical composition, mass, intrinsic luminosity, et cetera, et cetera. The combined apparent brightness of this cluster of stars, as I said, none of which are in the top 100, but when you combine all of these stars together in a cluster and look at it with your naked eye, the brightness gets to be within the range of the 10 brightest stars in all of heaven. You just have to integrate all of this light together. 5 of the stars are arranged in a little dipper configuration, and I think that should be obvious to you all. And below the handle is this curving line of stars. When I pointed this out to my grandson one night when we were looking at the constellation, he said, "You know, Grandpa, that looks like a boomerang." And from then on, he's convinced me that is a boomerang. And in the middle of the cup or saucer, if you will, are 2 stars that are fairly close together. And if we zoom in on those, oops, you'll see that the bottom of the 2 stars is starting to separate into a double. And we'll see that in a subsequent PowerPoint presentation we make in a few minutes. But do try to remember to look at the boomerang and see if your binoculars or telescope are good enough to suss out this double star. Altogether, if you get binoculars on this field, you'll see probably 2 to 3 dozen stars. And if you put them steady on a tripod and concentrate, I've been able to count up to 50 in the Pleiades, but astronomers have dug out that there's roughly 1,000 stars in this particular open star cluster. Let's back up and go to our another object. And I'm going to get rid of the names here for a minute. If you look, let's pull this cluster up. In good dark skies, you'll see a V, which goes from this bright star Aldebaran to the bottom of the V here to this star at the top. Let's zoom in here. Actually, I should have stayed on Aldebaran to pull it up. more towards the middle of the screen. This is also a open cluster of stars like the Pleiades. It was born roughly 625 million years ago, much, much older than the Pleiades. And binoculars, again, are best to view this really large cluster of stars because overall it encompasses roughly 6 degrees of the sky when you look at it. So a telescope wouldn't do it justice. But do look at the color of Aldebaran and compare it to the color of Betelgeuse. It should be washed out a little bit relative to that of Betelgeuse. It doesn't belong to this cluster. This cluster is roughly 150 light years away in this V configuration, and some of the ones within that configuration, but not along the same lines. Aldebaran is a little bit less than twice as far away, about 65 light years, but it's way older than the Hyades. It's a little bit over 6.5 billion years old. So this star was born, if you will, well before our solar system was formed. And I'd like to point out too, if you get your binoculars out, look at this nice looking double star. It's called Theta Tauri, and but they're not companions in the sense that they orbit about one another in a binary system. They're separated by about 4 light years, but as seen from Earth, they do present a really nice double. Let's back off. We're going to look a little bit at Orion. And we're going to look at the sword here. Oops, got to pull it up to the center, sorry. Now, with your naked eye, before you even get any optical aids out, if you've got good enough dark skies, you should see a fuzzy patch here in the middle of the sword, which is, or the sword scabbard, if you will, which is hanging below the 3 belt stars and at a slight angle askew from directly below them. And this is called the Orion Nebula. The 2 star clusters I just described to you before, the Hyades and the Pleiades, were also born in a nebula at the same time. People, you can think of stars as like cookies. They're formed in batches together in some sort of nebula. Let's zoom in on this nebula. And, whoops, sorry. If you look at this nebula with binoculars, you'll see 2 very, very bright stars. You won't see any colors. Your eye can't integrate colors quickly over the time period before you pull in another frame, but and your cones aren't receptive enough. So this is an astrophotograph of this portion of the sky. Within this nebula, astronomers have identified roughly more than approximately 2,000 stars that have been born within the last few million years. You've got clouds of collapsing gas and dust forming these protostars or newly being born stars, if you will. If you zoom in a little bit further, let's go to this brighter patch right here. And you need a telescope for this one. You could see those 2 stars before, as we said, in binoculars. But if you get a good telescope on the upper right hand of the 2 bright objects, you've got this trapezoidal configuration of stars. You need a telescope with at least 100x magnification, or maybe a little bit more. But these are brilliant, brilliant stars, bright, hot, young stars in this, what's called the Trapezium cluster, after the trapezoidal configuration. Let's back off a little bit. Sorry, wrong way. And if we go down the sword to this brightest star at the bottom of the sword, it's Iota Orionis, as it's called. But I just want to point out to you, and one thing our software doesn't do is keep the dim stars dim. When we start to zoom in, the dim stars get brighter and brighter. But this is probably 20 times to 40 times less bright than Iota Orionis. This little double star here, which you should be able to see with modest binoculars as long as you have them stabilized on a tripod. And when I pointed this double out to my young grandson, he just got really excited that he was able to see that. And we'll see it again in a view in our PowerPoint presentation. Let's back up, whoops, the other way. Before you leave the sword, do look at some of these star clusters just above the nebula, the Orion Nebula it's called, and then go up to, continue on with your binoculars, up to, let's back off a little bit more, to the belt stars. And our software again is failing us in terms of brightness. This middle star in the belt, Mintaka, Alnilam, is actually brighter than the two on either side of it. The name of the bright star on the left-hand side is Alnitak, and from the Arabic, that means string of pearls. And these indeed look like a string of pearls to us. Just a lovely constellation. On the far right-hand side is Mintaka. We're going to zoom in on it in a minute, but let's draw your attention to these fields of stars in the belt and just spend some leisure time with your binoculars to look at all these little bright stars. They're intense in the belt. And then with Mintaka, the far right-hand star, zoom in, whoops, gotta put it in the center of the screen or we'll zoom past it. It is a double star, so you can split that one too. I've had difficulty with binoculars, but with a modest telescopic view, you'll be able to split that one as well. All right, so do spend some time on a comfortable chair with your loved ones, get some binoculars out or a modest telescope and just have a good time with Orion. We are not going to talk about any other objects.
Paul,
yes.
Before you move on, I've got a couple of questions, and it's really appropriate for them right now,
go ahead.
as opposed to later. One of them is, how close together are the Trapezium stars in Orion Nebula?
All I know is that they do orbit about one another. They're theta A, B, C, and D, theta 1, A, B, C, and D. But in terms of physical closeness, I can't tell you. I'd have to go to the web to look that one up. Sorry.
Okay. And then the other one is, what power of binoculars do you suggest? You've mentioned binoculars several times now, and you might also mention tripods and image stabilizing things and so on.
Yeah, we had a little show about that last month, the December show, but I find my 9-year-old grandson, who's not a really big kid, can easily handle, if he's sitting in a chair with some armrests for his elbows, he can easily handle my 15 by 70 Celestron binoculars. They're called Celestron Skymaster. And you can get the inexpensive version for roughly under $100, or you can get the more expensive Pro version for roughly around $200. And that's got some coatings for the optics that just reduces the glare a little bit. But just to get you started, stick to something that's inexpensive. 12 by 50s or 10 by 50s would be appropriate. They're going to be easier for a small person to hold. And in fact, my 9-year-old with his elbows braced, a 9-year-old grandson, can handle my 20 by 80s, believe it or not. So he does pretty good. I think once you start to get enthusiastic about what you're looking at, you don't get tired very fast. The other night I got cold, but he was out there for probably an extra half an hour after I went in. I kept going out and checking with him, but he just has a good time with those 15 by 70s. So I hope that answers some of the questions.
That's great. Yeah,
Yeah.
thank you for taking the time.
Oh, no problem. Any others?
Um,
I'll,
when
I'll,
Galen is faster than I am with Wikipedia, we're both um, having a contest to see who can get to it first, and Galen won. He said the trapezium stars are with 1.5 light years of each other.
okay, good. Ah, some of them may only be binocular doubles. You'd think they'd be orbiting about one another since they were born all about the same time, but maybe not. I don't know. Okay, let's exit this. Let's get to the PowerPoint portion of the show because time is moving. All right. Okay, before we even talk about anything else in terms of optical aids, let's talk about using your naked eye. And one of the really attractive things you can look at with your friends and loved ones is the scintillation of some of these very bright stars. Here is a photograph taken over several minutes, I think, of Sirius as it moves about through the sky. And while it's moving about through the sky, it's scintillating in different colors and popping around a little bit in the field of view. You can see it's going up, down, etc. If you look at Sirius in binoculars, you'll get an even bigger impression because you're going to be gathering more light. And the other star, its companion star, Procyon, in the Canis Minor constellation, and is going to be scintillating at the same time as Sirius. When Sirius and Procyon are low on the eastern horizon, and that's roughly 7:30 to 8 p.m. This evening and subsequent evenings early in this month. And the reason you get this scintillation is you've got, especially low on the horizon, is you've got different density layers in the atmosphere and pockets that cause the light coming from a distant object to be refracted very quickly. And the reason you see the colors is the cones in the cone photoreceptors in the back of your eye need enough light to be stimulated. Generally, only the rods are stimulated in a dark sky, but if you've got a really bright object like Sirius or Procyon, some of those in the top 10, they're always going to be scintillating in general on the when they're low on the horizon. Okay, let's move on. Here's that Pleiades star cluster without overexposure. And this is more like what you would see in a pair of binoculars. And here is below the brightest star, Alcyone is its name, is that boomerang collection of stars. And you can see the nice split in the double of the two in the center of the cup. Hyades star cluster again, we're just doing a quick repeat. If you do get your binoculars out to look at it, look at the double here, it's called Theta Tauri. And again, as I said, they don't orbit about one another in a binary configuration. They're just along the same line of sight as seen from Earth. And remember again, Aldebaran doesn't belong to this cluster. It's not a member. It's not moving along with the cluster through the sky. But it's conveniently placed at the top of, or bottom, I should say, of this lazy V. For the sword, here's an astrophotograph without the overexposure to give you light. And again, you can see the difference in the brightness of this double star below Iota Orionis, as it's called. And it's several times dimmer than Iota Orionis. And then what looks like a single star up here, when you look at the sword, is really 2 or 3 in close proximity. And then this beautiful field of view when, remember I said, get your binoculars out and just cruise around through the belt. And remember I also said that our software doesn't do justice to the star field and also to the middle star, Alnilam, in the belt, because it is brighter than the other two by just a little bit. So just spend some time cruising through that portion of the sky slowly, and then go out beyond the belt up and to the right. You'll see another more beautiful star fields. Okay, let's have a couple more really intense views of the Orion Nebula. Here's the trapezium as seen in the visible spectrum through the Hubble Space Telescope. And then if we go to infrared, which the Hubble is capable of doing, infrared light can penetrate through clouds of dust and gas and look at objects below what you would quote unquote call the surface of the nebula. And this is how astronomers have been able to identify so many other stars within the nebula. And you can see there's just a whole bunch of them being born at the same time. And in addition to that, you've got stars that are still being formed in collapsing clouds of gas and dust. These are protostars. Some of them have started to get enough gravitational collapse that they're starting to light at the center. Some are not. But surrounding them are clouds of dust forming what we call protoplanetary disks or nascent disks or spheres. The spheres will eventually collapse into disks, and eventually some of those disks will have planets orbiting about their host star, if you will. And this protoplanetary disk illustrated here from the Hubble is right next to the trapezium cluster. All right, so here we've got a Stellarium software view of the Winter Hexagon, as we called it, with the lines appropriately drawn in. It's not, as we said, not actually doesn't mimic a hexagon that closely. It, to some of you football fans, it looks more like an American football. But here are the names of those 5 stars that are in the top 10. And then here, and in the order, as we said, Sirius is number 1, but if you want to remember the order of the other 4 stars, just remember Carp Bone. Capella is number 6, Rigel is 7, Procyon is 8, and Betelgeuse is either 9th or 10th, depending on how much light it puts out. It's a very variable star. Beyond that, you've got the other 3 stars, Aldebaran, Pollux, and Castor. And as I said, all of these are in the top 25 brightest stars. So back here, you've got the 50% of all the 10 brightest stars in the heavens and 25%, or sorry, 33% of the 25 brightest stars in the skies, these 8. All right, we're going to quickly look at some observations that astronomers have made over the centuries to determine whether or not these stars we see with our naked eye are singles or doubles or whatever. Do they have companion stars? Yes, the answer is yes. And Castor A and B were discovered back in 1718 by an English astronomer named James Pound. It was the first record that we can find historically where an astronomer has listed seeing this companion star. And if you can't tell from the photograph, the companion star, Castor B, the dimmer one, is 2.5 times dimmer than the primary star. The next toughest one to suss out was Rigel, listed as Rigel A and B now. And Rigel B, you can see, is much dimmer than the parent star, and its brightness now is 440 times dimmer than the parent star. And the astronomer that discovered this double was the very famous astronomer William Herschel. We know him as the discoverer of the planet Uranus back in early 1781. But later that year, around December, he really wanted to be the first astronomer that determined could accurately measure distances to what we call the fixed stars. We got that in quotes because we know now they're not fixed. And he stated that he would have a three-pronged effort in this pursuit. He was going to catalog the positions of every double star within the northern hemisphere. And he cataloged the positions of roughly over 1,000 of these star pairs. He was only going to select narrowly spaced pairs with large brightness variations. And back then, astronomers thought all of the stars in the skies were essentially clones of our sun. So basically, if a star was dimmer than another star, it was further away. So hence the quote, faintness equals farness, if everything is a clone. And then he was going to repeat these measurements over many years and see if he could detect any semi-annual wobble, which would occur when the Earth is on one side of its orbit around the sun versus the other side. Galen, I talked to him, and he's going to go into the details of parallax and how you find these distances in his talk next week. So I strongly encourage you to attend that talk. So what happened? After roughly 20 years, he kept inspecting many of these double star systems, and he noted that several of them revealed unmistakably that most double stars were orbiting about one another. And that was made him crestfallen, but he also, it turned out, discovered one very important thing, that he showed that Newton's laws of gravity and motion operated well beyond the solar system. So now we call them Newton's universal law of gravitation. Before that time, people had no proof that Newton's law of gravitation worked anywhere except outside the solar system, nor did they have any proof that Kepler's laws of planetary motion were valid either, except in the solar system. So let's continue on with our pursuit of companion stars. I'm going to keep moving pretty quickly here. The first man to really discover the distance to a nearby star was Friedrich Wilhelm Bessel, a German astronomer, and he observed wobbles in the positions of both Sirius and Procyon while he was trying to determine the first stellar distance confirmation, if you will. He speculated that the wobbles that he observed meant they had unseen companions. And the wobbles he observed would be because you've got one dimmer object orbiting the brighter object, and they orbit about a common center of mass, which I don't know if you can see it or not, but is this little crosshatch, not quite at the center. It keeps oscillating around the center of that star as its companion is orbiting about it. Now, so it took another almost 20 years before astronomers had equipment powerful enough to suss out the dimmer of the two stars in Sirius, and that was Sirius B, and it was much, much dimmer. It's like 10,000 times dimmer than Sirius A. And it took, at that time, in 1862, the largest refracting telescope in the world, made by the company headed by a man named Clark, which eventually went to the Dearborn Planetarium. But that was the telescope used to identify Sirius B. And it's affectionately known by astronomers as the pup. And finally, Procyon, the other wobbling star, had an even dimmer companion, 15,000 times dimmer. So we're starting to get to the point where you're trying to look at the light of a firefly next to a lighthouse. And again, the largest telescope, refracting telescope at that time in the world was used to find Procyon B in 1896. How about any other stars that are too close to see optically? Well, whoops, sorry, before I get to that. After Bessel found the distances to a nearby star, other astronomers got on the bandwagon. Astrophotography was invented about 1850. Daguerre invented photography in the 40s, and then 1850s, astronomers started to look at objects and photograph them in the heavens. I think Vega was the first star ever photographed. At any rate, over many, many decades, if not hundreds of years, many stars, and in fact, with the Hipparcos satellite in the 1990s, late 1980s, 1990s, 120,000 stellar distances were categorized or calculated. And you can see Sirius, very close to us, not the closest star, but it is fairly close. And then Rigel is roughly 100 times further away. So you've got a huge difference in distances for all of these stars that are comparable in brightness. So it's a combination of the distance and their intrinsic brightness that determines how bright we see them here on Earth. Okay, how does one spot objects that are orbiting really close to a nearby star? Galen, I'm sure we'll get into this next week, but it's basically a view of a spectrum of a star with a planet, high mass planet orbiting about it. And as the star orbits away from us around its center mass, or towards us right now, it's a blue shift. And then as it goes away, the spectrum moves to the right. It's a red shift, blue shift. This is just for detecting exoplanets. But if you had two stars and you looked at their spectra concurrently, you'd see their spectra swapping places as they orbit about one another. We're almost out of time, so I'm going to skip a lot of these other slides, but I'm going to spend, by the way, Capella was first determined to be a spectroscopic binary, as it's called, in 1899. And we'll just spend a few seconds on these slides. I won't discuss them in detail at all because the show is being recorded, as Rick said, and then you can view these at your own leisure. This is one I had to make on my own because, and I apologize for that, but I couldn't find a good artistic rendering of the Rigel system, and there's 4 stars in the Rigel system, as there are 4 in the Capella system. And in Castor, that's remember Castor was the first star to be split by astronomers, but spectroscopically, they found other stars orbiting Castor A and B, and then there was another red dwarf pair discovered subsequently. So you got 6 stars, and all of these are compared to the size of the sun. Here are the components listed for the Winter Hexagon, major stars. How many of them are there? And also, 2 of those stars, single stars, Aldebaran and Pollux, each have one, I think one is a 2.5 Jupiter mass, and the other is a 5 Jupiter mass star orbiting about them. And the ages vary all over the map, but we go from Betelgeuse and Rigel, which are the youngest stars, only roughly about 8 million years old, to Aldebaran, which is, like I said, older than the formation of our solar system. Here's a slide I made to just give you a gee whiz size comparison of the stars. Galen will probably get into why they get bigger with time, with increasing fractions of their lifetime, I should say. And this is compared to our sun on the same scale. Aldebaran is roughly 43 to 45 times as big as our sun in diameter. And the intrinsic diameter of Rigel is about 75 times the diameter of our sun. Rigel, if we're placed where our sun is, would nearly touch the orbit of Mercury. But the big boy in all of this is Betelgeuse, which this is an actual image taken by the ALMA array in Chile, a large millimeter array, and the outer surface of Betelgeuse, if we're put at the where the sun is, would reach out to the orbit of Jupiter. It's a monster. It's 1,000 times larger than our sun approximately, and it's oscillating all the time. So we're near the end of the hour, so I'm going to quit there and just move on to this lovely quote by Johannes Kepler. And I'll let you read that on your own. I just want to to encourage you that the beauty that you see in the night skies is always more complex, as we tried to illustrate in this talk, and wonderful than anything we can imagine. And the words of Kepler certainly reinforce that you'll get many intellectual rewards while pursuing details of various objects in the night skies. And with that, we'll stop. Rick, any other questions?
Yes, we do have a couple questions. The first one is, do double stars have a common source material from which they both develop, or even
Yeah.
multiple star systems?
Oh, sorry, go ahead.
Yeah, go ahead.
As I said, the stars are like cookies. They're formed in batches, and they're formed around the same time. It'll vary by a million years or more. But like we see with the Orion Nebula, this monkey head nebula, by the way, is another nebula where stars are being born. And this is also in the constellation Orion. So yes, it would be a very rare case for a star to have a star come so close to it that it would grab it and form a binary pair. Most of these, if not 99.999%, are brothers and or sisters, if you will, born out of the same parent nebula.
Okay. And you actually briefly mentioned one of your diagrams that was related to the exoplanets. Are there double or triple star systems that have planets around them?
Oh yeah, if you go to the European Space Agency website, which has a link to exoplanets, there's another link that talks about multiple planet systems, as well as planets around double, triple, and quadruple star systems. So yes, that is the answer. And I'm sure that there are exoplanets around some of those stars in the Winter Hexagon that we didn't list as having exoplanets around them. But, you know, when you've got this complex spectroscopy going on, it's difficult enough to get the signal from the noise when you've got multiple stars, and even tougher to get signal from noise or if you've got a complex system. But there have been instances of those being recorded, and you'll find those on the European Space Agency organization's website.
You might even mention Alpha Centauri.
Oh yeah, sorry. Yeah, the closest star to us, 4.25 light years away, is the Alpha Centauri system, and the very closest star to us is a red dwarf, Proxima Centauri. And by the way, the red dwarfs are tough to find. Astronomers didn't find Proxima Centauri or discover it until about 1916. But because they are very, very dim. And Galen will go into those details next week. But an exoplanet has been discovered orbiting about Proxima Centauri, as it's called, the closest star to our solar system. So yes, that is a triple. Sorry, I forgot about that. But if you look at lovely artistic renderings of Proxima Centauri b, as the planet's called, it's in what's called the Goldilocks zone, where water could exist if it were on the surface of that planet. And there's a lovely artist drawing of Alpha Centauri A and B, the double stars, which are just, both of those stars are just slightly bigger, and one is slightly bigger, more massive than our sun, and one is slightly smaller, but they're comparable to our sun in terms of brightness and size, etc.
Interesting. So if it were a desert-like planet, it might even look a little bit like Tatooine from Star Wars for our Star Wars
Oh
fans.
yeah, except you, yeah, exactly. Yeah.
Uh, okay, so the I was about to dump something on Galen, but I think I better not. Um, well, sure, what the heck, he can do it. So Edward Fitzgerald, I hope Edward you're going to be around next week. Asks, given the common source material, why the variance in brightness between different stars? And I should mention that Galen has already said Paul has given me much too much, many details to go into, so we'll see what he can do next week. But this one is really right down Galen's alley here. But anyway, I'll let you mention a few words about this. Given common source material, why the variance in brightness?
Because stars, as you saw in those uh, binary, quadruple, and septuple systems, you've got stars of different size or mass being born. And the larger the mass of a star, the more, you've got more gravity wanting to collapse that star. And so it's being crushed. And what it has to do to counteract the gravitational force is use radiation pressure from its core. Otherwise, the collapse will continue on indefinitely. And the radiation pressure varies at the core depending on the mass of the star. The bigger the stellar mass, the hotter the temperature in the center, the faster fuel is being burned. Fuel gets burned at roughly a rate of it's 3.5 times the mass of the star, or yeah, 3.5 times the mass of the star. So if it's very low mass star, those stars can last for a long time. Our own sun is going to last roughly 10 billion years. But because Betelgeuse is somewhere between 15 and 25 times the mass of our star, it's burning hot and young, and it is projected to go supernova within the next 200,000 to million years. Rigel will follow behind it pretty quickly because it's a 21 solar mass star. But like Proxima Centauri, I think it's somewhere around a half a solar mass. I'm sorry, I don't remember the number exactly. But that means it's going to be lasting many, many, many billions of years. And some of these stars are projected with very low mass to last up to as much as 1 trillion years, way beyond the age of the universe. Sorry, I'll let Galen weigh in if he wants to.
As a matter of fact, Galen has already commented that he actually will talk more about that, exactly that question of why different stars are different brightnesses and different masses and luminosities and so on. So I hope Ed can join us next week for Galen's talk. Okay, those are all the questions that came in from viewers. Paul, thank you again so much for sharing with us tonight. We urge you all to go out over the next few days and look into the sky in the evening or the early morning and see which of these things you can identify that Paul has talked about today. Next week, Galen Giesler will join us, as Paul has said, to discuss star clusters and the color of stars. Enjoy the dark nights of the winter season, and we hope to see you again soon. Good night, everyone.
Thank you all.